Diamond is a solid form of the element carbon with its atoms arranged in a crystal structure called diamond cubic. At room temperature and pressure, another solid form of carbon known as graphite is the chemically stable form of carbon, but diamond almost never converts to it. Diamond has the highest hardness and thermal conductivity of any natural material, properties that are utilized in major industrial applications such as cutting and polishing tools. They are also the reason that diamond anvil cells can subject materials to pressures found deep in the earth. Because the arrangement of atoms in diamond is extremely rigid, few types of impurity can contaminate it, two exceptions being boron and nitrogen. Small numbers of defects or impurities, about 1 per million of lattice atoms, color diamond blue, boron, yellow, nitrogen, brown, defects, green, radiation exposure, purple, pink, orange, or red. Diamond also has relatively high optical dispersion, ability to disperse light of different colors. Most natural diamonds have ages between 1 billion and 3.5 billion years. Most were formed at depths between 150 and 250 kilometers, 93 and 155 mi, in the Earth's mantle, although a few have come from as deep as 800 kilometers, 500 mi. Under high pressure and temperature, carbon-containing fluids dissolved various minerals and replaced them with diamonds. Much more recently, tens to hundreds of million years ago, they were carried to the surface in volcanic eruptions and deposited in igneous rocks known as kimberlites and lamproites. Synthetic diamonds can be grown from high-purity carbon under high pressures and temperatures, or from hydrocarbon gas by chemical vapor deposition, CVD. Imitation diamonds can also be made out of materials such as cubic zirconia and silicon carbide. Natural, synthetic and imitation diamonds are most commonly distinguished using optical techniques or thermal conductivity measurements. Material properties. Main article, Material properties of diamond. Diamond is a solid form of pure carbon with its atoms arranged in a crystal. Solid carbon comes in different forms, known as allotropes depending on the type of chemical bond. The two most common allotropes of pure carbon are diamond and graphite. In graphite the bonds are sp2 orbital hybrids and the atoms form in planes with each bound to three nearest neighbors 120 degrees apart. In diamond they are sp3 and the atoms form tetrahedra with each bound to four nearest neighbors. 3-4 tetrahedra are rigid, the bonds are strong, and of all known substances diamond has the greatest number of atoms per unit volume, which is why it is both the hardest and the least compressible. 5-6 It also has a high density, ranging from 3150 to 3530 kilograms per cubic meter, over 3 times the density of water, in natural diamonds and 3520 kilograms M3 in pure diamond. 1 In graphite, the bonds between nearest neighbors are even stronger, but the bonds between planes are weak, so the planes easily slip past each other. Thus, graphite is much softer than diamond. However, the stronger bonds make graphite less flammable. 7 Diamonds have been adapted for many uses because of the material's exceptional physical characteristics. Of all known substances, it is the hardest and least compressible. It has the highest thermal conductivity and the highest sound velocity. It has low adhesion and friction, and its coefficient of thermal expansion is extremely low. Its optical transparency extends from the far infrared to the deep ultraviolet and it has high optical dispersion. It also has high electrical resistance. It is chemically inert, not reacting with most corrosive substances, and has excellent biological compatibility. 8 Thermodynamics theoretically predicted phase diagram of carbon. The equilibrium pressure and temperature conditions for a transition between graphite and diamond are well established theoretically and experimentally. The pressure changes linearly between 1.7 Pa at 0 K and 12 Pa at 5000 K. The diamond graphite liquid triple point. 9-10 However, the phases have a wide region about this line where they can coexist. At normal temperature and pressure, 20 degrees centigrade, 293 K, and 1 standard atmosphere, 0.10 Pa, the stable phase of carbon is graphite, but diamond is metastable and its rate of conversion to graphite is negligible. 6 However, at temperatures above about 4500 K, diamond rapidly converts to graphite. Rapid conversion of graphite to diamond requires pressures well above the equilibrium line. At 2000 K, a pressure of 35 Pa is needed. 9 Above the triple point, the melting point of diamond increases slowly with increasing pressure. But at pressures of hundreds of Pa, it decreases. 11 At high pressures, silicon and germanium have a BCC body-centered cubic crystal structure, and a similar structure is predicted for carbon at high pressures. At 0 K, the transition is predicted to occur at 1100 Pa. Research results published in an article in the scientific journal Nature in 2010 suggest that at ultra-high pressures and temperatures, about 10 million atmospheres or 1 Pa and 50,000 degrees centigrade, diamond behaves as a metallic fluid. The extreme conditions required for this to occur are present in the gas giants Neptune and Uranus. Both planets are made up of approximately 10% carbon and could hypothetically contain oceans of liquid carbon. Since large quantities of metallic fluid can affect the magnetic field, this could serve as an explanation as to why the geographic and magnetic poles of the two planets are unaligned. 1314 Crystal structure. See also crystallographic defects in diamond unit cell, showing the tetrahedral structure. The most common crystal structure of diamond is called diamond cubic. It is formed of unit cells. See the figure, stacked together. Although there are 18 atoms in the figure, each corner atom is shared by 8 unit cells, and each atom in the center of a face is shared by 2, so there are a total of 8 atoms per unit cell. 15 Each side of the unit cell is 3.57 angstroms in length. 16 A diamond cubic lattice can be thought of as two interpenetrating face-centered cubic lattices, with one displaced by 1/4 of the diagonal along a cubic cell, or as one lattice with two atoms associated with each lattice point. 16 Viewed from a 111 crystallographic direction, it is formed of layers stacked in a repeating ABC pattern. Diamonds can also form an abab structure, which is known as hexagonal diamond or lansdaleite, but this is far less common and is formed under different conditions from cubic carbon. 17 Crystal habit. One face of an uncut octahedral diamond, showing trigones of positive and negative relief, formed by natural chemical etching. Diamonds occur most often as euhedral or rounded octahedra and twinned octahedra known as McLeS. As diamond's crystal structure has a cubic arrangement of the atoms, they have many facets that belong to a cube: octahedron, rhombicosododecahedron, tetrachus, hexahedron, or dysdiachus dodecahedron. The crystals can have rounded off and unexpressive edges and can be elongated. Diamonds, especially those with rounded crystal faces, are commonly found coated in NIF, an opaque gum-like skin. 18 Some diamonds contain opaque fibers. They are referred to as opaque if the fibers grow from a clear substrate or fibrous if they occupy the entire crystal. Their colors range from yellow to green or gray, sometimes with cloud-like white to gray impurities. Their most common shape is cuboidal, but they can also form octahedra, dodecahedra, McLeS, or combined shapes. The structure is the result of numerous impurities with sizes between 1 and 5 microns. These diamonds probably formed in kimberlite magma and sampled the volatiles. 19 Diamonds can also form polycrystalline aggregates. There have been attempts to classify them into groups with names such as Bort-Ballas, Stuartite, and Framosite, but there is no widely accepted set of criteria. 19 Carbonado, a type in which the diamond grains were sintered fused without melting by the application of heat and pressure, is black in color and tougher than single crystal diamond. 20 It has never been observed in a volcanic rock. There are many theories for its origin, including formation in a star, but no consensus. 19 21 22 Mechanical properties. Hardness. The extreme hardness of diamond in certain orientations makes it useful in materials science, as in this pyramidal diamond embedded in the working surface of a Vickers hardness tester. Diamond is the hardest known natural material on both the Vickers scale and the Mohs scale. Diamond's great hardness relative to other materials has been known since antiquity and is the source of its name. This does not mean that it is infinitely hard, indestructible, or unscratchable. 23 Indeed, diamonds can be scratched by other diamonds. 24 And worn down over time, even by softer materials, such as vinyl phonograph records. Diamond hardness depends on its purity, crystalline perfection, and orientation. Hardness is higher for flawless pure crystals oriented to the 111 direction, along the longest diagonal of the cubic diamond lattice. 26 Therefore, whereas it might be possible to scratch some diamonds with other materials, such as boron nitride, the hardest diamonds can only be scratched by other diamonds, and nanocrystalline diamond aggregates. The hardness of diamond contributes to its suitability as a gemstone. Because it can only be scratched by other diamonds, it maintains its polish extremely well. Unlike many other gems, it is well suited to daily wear, because of its resistance to scratching, perhaps contributing to its popularity as the preferred gem in engagement or wedding rings, which are often worn every day. The hardest natural diamonds mostly originate from the Copton and Bingara fields located in the New England area in New South Wales, Australia. These diamonds are generally small, perfect to semi-perfect octahedra, and are used to polish other diamonds. Their hardness is associated with the crystal growth form, which is single-stage crystal growth. Most other diamonds show more evidence of multiple growth stages, which produce inclusions, flaws, and defect planes in the crystal lattice, all of which affect their hardness. It is possible to treat regular diamonds under a combination of high pressure and high temperature to produce diamonds that are harder than the diamonds used in hardness gauges. Tenesomwhat related to hardness is another mechanical property, toughness, which is a material's ability to resist breakage from forceful impact. The toughness of natural diamond has been measured as 7.510 MPa.m². 2829. This value is good compared to other ceramic materials, but poor compared to most engineering materials such as engineering alloys, which typically exhibit toughnesses over 100 MPa.m². As with any material, the macroscopic geometry of a diamond contributes to its resistance to breakage. Diamond has a cleavage plane and is therefore more fragile in some orientations than others. Diamond cutters use this attribute to cleave some stones prior to faceting. 30 Impact toughness is one of the main indexes to measure the quality of synthetic industrial diamonds. Yield strength diamond has compressive yield strength of 130–140 Pa. 31 This exceptionally high value, along with the hardness and transparency of diamond, are the reasons that diamond anvil cells are the main tool for high-pressure experiments. 32 These anvils have reached pressures of 600 Pa. 33 Much higher pressures may be possible with nanocrystalline diamonds. 32–34 Elasticity and tensile strength Usually, attempting to deform bulk diamond crystal by tension or bending results in brittle fracture. However, when single crystalline diamond is in the form of micro-nanoscale wires or needles, 100–300 nanometers in diameter, micrometers long, they can be elastically stretched by as much as 9–10% tensile strain without failure. 35 With a maximum local tensile stress of 89–98 Pa. 36 Very close to the theoretical limit for this material. 37 Electrical conductivity. Other specialized applications also exist or are being developed, including use as semiconductors. Some blue diamonds are natural semiconductors, in contrast to most diamonds, which are excellent electrical insulators. The conductivity and blue color originate from boron impurity. Boron substitutes for carbon atoms in the diamond lattice, donating a hole into the valence band. 38 Substantial conductivity is commonly observed in nominally undoped diamond grown by chemical vapor deposition. This conductivity is associated with hydrogen-related species adsorbed at the surface, and it can be removed by annealing or other surface treatments. 3940 A 2020 paper reported that extremely thin needles of diamond can be made to vary their electronic band gap from the normal 5.6 eV to near zero by selective mechanical deformation. 41 Surface property. Diamonds are naturally lipophilic and hydrophobic, which means the diamond surface cannot be wet by water, but can be easily wet and stuck by oil. This property can be utilized to extract diamonds using oil when making synthetic diamonds. However, when diamond surfaces are chemically modified with certain ions, they are expected to become so hydrophilic that they can stabilize multiple layers of water ice at human body temperature. 42 The surface of diamonds is partially oxidized. The oxidized surface can be reduced by heat treatment under hydrogen flow. That is to say, this heat treatment partially removes oxygen-containing functional groups. But diamonds, sp3c, are unstable against high temperature, above about 400 degrees centigrade, 752 degrees Fahrenheit, under atmospheric pressure. The structure gradually changes into sp2c above this temperature. Thus, diamonds should be reduced under this temperature. 43 Chemical stability at room temperature. Diamonds do not react with any chemical reagents including strong acids and bases. In an atmosphere of pure oxygen, diamond has an ignition point that ranges from 690 degrees centigrade, 1274 degrees Fahrenheit, to 840 degrees centigrade, 1540 degrees Fahrenheit. Smaller crystals tend to burn more easily. It increases in temperature from red to white heat and burns with a pale blue flame and continues to burn after the source of heat is removed. By contrast, in air the combustion will cease as soon as the heat is removed because the oxygen is diluted with nitrogen. A clear, flawless, transparent diamond is completely converted to carbon dioxide. Any impurities will be left as ash. 44 Heat generated from cutting a diamond will not ignite the diamond. 45 And neither will a cigarette lighter. 46 But house fires and blow torches are hot enough. Jewelers must be careful when molding the metal in a diamond ring. 47 Diamond powder of an appropriate grain size, around 50 microns, burns with a shower of sparks after ignition from a flame. Consequently, pyrotechnic compositions based on synthetic diamond powder can be prepared. The resulting sparks are of the usual red-orange color, comparable to charcoal, but show a very linear trajectory which is explained by their high density. 48 Diamond also reacts with fluorine gas above about 700 degrees centigrade, 1292 degrees Fahrenheit. Color Main article. Diamond color. Brown diamonds at the National Museum of Natural History in Washington, D.C. The most famous colored diamond, the Hope Diamond has a wide band gap of 5.5 eV corresponding to the deep ultraviolet wavelength of 225 nanometers. This means that pure diamond should transmit visible light and appear as a clear colorless crystal. Colors in diamond originate from lattice defects and impurities. The diamond crystal lattice is exceptionally strong, and only atoms of nitrogen, boron, and hydrogen can be introduced into diamond during the growth at significant concentrations, up to atomic percents. Transition metals nickel and cobalt, which are commonly used for growth of synthetic diamond by high-pressure high-temperature techniques, have been detected in diamond as individual atoms. The maximum concentration is 0.01% for NiCkel49 and even less for cobalt. Virtually any element can be introduced to diamond by ion implantation. 50 Nitrogen is by far the most common impurity found in gem diamonds and is responsible for the yellow and brown color in diamonds. Boron is responsible for the blue color. 51 Color in diamond has two additional sources: irradiation, usually by alpha particles, that causes the color in green diamonds, and plastic deformation of the diamond crystal lattice. Plastic deformation is the cause of color in some BROWN 52 and perhaps pink and red diamonds. 53 In order of increasing rarity. Yellow diamond is followed by brown, colorless, then by blue, green, black, pink, orange, purple, and red. 30 Black, or carbonado. Diamonds are not truly black, but rather contain numerous dark inclusions that give the gems their dark appearance. Colored diamonds contain impurities or structural defects that cause the coloration, while pure or nearly pure diamonds are transparent and colorless. Most diamond impurities replace a carbon atom in the crystal lattice, known as a carbon flaw. The most common impurity, nitrogen, causes a slight to intense yellow coloration, depending upon the type and concentration of nitrogen present. 30 The Gemological Institute of America (GEA) classifies low saturation yellow and brown diamonds as diamonds in the normal color range and applies a grading scale from D, colorless, to Z, light yellow. Diamonds of a different color, such as blue, are called fancy colored diamonds and fall under a different grading scale. 30 In 2008, the Wittelsbach diamond, a 35.56 carat, 7.112 grams blue diamond once belonging to the King of Spain, fetched over US $24 million at a Christie's auction. 54 In mid-2009, a 7.03 carat, 1.406 grams blue diamond fetched the highest price per carat ever paid for a diamond when it was sold at auction for 10.5 million Swiss francs, 6.97 million euros, or US $9.5 million at the time. 55 That record was, however, beaten the same year. A 5-carat 1.0 grams vivid pink diamond was sold for $10.8 million in Hong Kong on December 1, 2009. 56 Identification diamonds can be identified by their high thermal conductivity, 92320W.M1.K1. 57 Their high refractive index is also indicative, but other materials have similar refractivity. Diamonds cut glass, but this does not positively identify a diamond because other materials, such as quartz, also lie above glass on the Mohs scale and can also cut it. Diamonds can scratch other diamonds, but this can result in damage to one or both stones. Hardness tests are infrequently used in practical gemology because of their potentially destructive nature. 58 The extreme hardness and high value of diamond means that gems are typically polished slowly, using painstaking traditional techniques and greater attention to detail, than is the case with most other gemstones. 59 These tend to result in extremely flat, highly polished facets, with exceptionally sharp facet edges. Diamonds also possess an extremely high refractive index and fairly high dispersion. Taken together, these factors affect the overall appearance of a polished diamond, and most diamanters still rely upon skilled use of a loupe magnifying glass to identify diamonds. By I.60 geology, diamonds are extremely rare, with concentrations of at most parts per billion in source rock. 19 Before the 20th century, most diamonds were found in alluvial deposits. Loose diamonds are also found along existing and ancient shorelines, where they tend to accumulate because of their size and density. 61 149 Rarely, they have been found in glacial till, notably in Wisconsin and Indiana, but these deposits are not of commercial quality. 61 19 These types of deposit were derived from localized igneous intrusions through weathering and transport by wind or water. 62 Most diamonds come from the Earth's mantle, and most of this section discusses those diamonds. However, there are other sources. Some blocks of the crust, or terranes, have been buried deep enough as the crust thickened, so they experienced ultra-high pressure metamorphism. These have evenly distributed microdiamonds that show no sign of transport by magma. In addition, when meteorites strike the ground, the shock wave can produce high enough temperatures and pressures for microdiamonds and nanodiamonds to form. 62 Impact-type microdiamonds can be used as an indicator of ancient impact craters. 63 Popokai crater in Russia may have the world's largest diamond deposit, estimated at trillions of carats, and formed by an asteroid impact. 64 A common misconception is that diamonds form from highly compressed coal. Coal is formed from buried prehistoric plants, and most diamonds that have been dated are far older than the first land plants. It is possible that diamonds can form from coal in subduction zones, but diamonds formed in this way are rare, and the carbon source is more likely carbonate rocks and organic carbon and sediments, rather than coal. 65-66 Surface distribution geologic provinces of the world. The pink and orange areas are shields and platforms, which together constitute cratons. Diamonds are far from evenly distributed over the Earth. A rule of thumb known as Clifford's rule states that they are almost always found in kimberlites on the oldest part of cratons, the stable cores of continents with typical ages of 2.5 billion years or more. 62-67 314 However, there are exceptions. The Argyle Diamond Mine in Australia, the largest producer of diamonds by weight in the world, is located in a mobile belt, also known as an orogenic belt. 68 A weakers. A marketing. Diamond balance scale 0.0125 carats. Jewelers measuring tool marketing has significantly affected the image of diamond as a valuable commodity. NWAR & Son, the advertising firm retained by De Beers in the mid-20th century, succeeded in reviving the American diamond market, and the firm created new markets in countries where no diamond tradition had existed before. NWAR's marketing included product placement, advertising focused on the diamond product itself rather than the De Beers brand, and associations with celebrities and royalty. Without advertising the De Beers brand, De Beers was advertising its competitors' diamond products as well. 108 But this was not a concern, as De Beers dominated the diamond market throughout the 20th century. De Beers' market share dipped temporarily to second place in the global market below El Rosa in the aftermath of the global economic crisis of 2008, down to less than 29% in terms of carats mined, rather than sold. 109 The campaign lasted for decades, but was effectively discontinued by early 2011. De Beers still advertises diamonds, but the advertising now mostly promotes its own brands or licensed product lines rather than completely generic diamond products. 109 The campaign was perhaps best captured by the slogan "A diamond is forever." 110 The slogan is now being used by De Beers Diamond Jewelers. 111 A jewelry firm which is a 50% joint venture between the De Beers Mining Company and LVMH, the luxury goods conglomerate. Brown-colored diamonds constituted a significant part of the diamond production and were predominantly used for industrial purposes. They were seen as worthless for jewelry, not even being assessed on the diamond color scale. After the development of Argyle Diamond Mine in Australia in 1986 and marketing, Brown diamonds have become acceptable gems. 112-113 The change was mostly due to the numbers. The Argyle mine, with its 35 million carats, 7,000 kilograms, of diamonds per year, makes about one-third of global production of natural diamonds. 114-80% of Argyle diamonds are brown. 115 Industrial-grade diamonds. A scalpel with synthetic diamond blade. Close-up photograph of an angle grinder blade with tiny diamonds shown embedded in the metal-88 diamond knife blade used for cutting ultra-thin sections, typically 70 to 350 nm. For transmission electron microscopy, industrial diamonds are valued mostly for their hardness and thermal conductivity, making many of the gemological characteristics of diamonds, such as the 4CS, irrelevant for most applications. 80% of mined diamonds, equal to about 135 million carats, 27,000 kilograms, annually, are unsuitable for use as gemstones and are used industrially. 116 In addition to mined diamonds, synthetic diamonds found industrial applications almost immediately after their invention in the 1950s. Another 570 million carats, 114,000 kilograms, of synthetic diamond is produced annually for industrial use in 2004. In 2014 it is 4,500 million carats, 900,000 kilograms, 90% of which is produced in China. Approximately 90% of diamond grinding grid is currently of synthetic origin. 117. The boundary between gem-quality diamonds and industrial diamonds is poorly defined and partly depends on market conditions. For example, if demand for polished diamonds is high, some lower-grade stones will be polished into low-quality or small gemstones, rather than being sold for industrial use. Within the category of industrial diamonds, there is a subcategory comprising the lowest quality, mostly opaque stones, which are known as bort. 118 Industrial use of diamonds has historically been associated with their hardness, which makes diamond the ideal material for cutting and grinding tools. As the hardest known naturally occurring material, diamond can be used to polish, cut, or wear away any material, including other diamonds. Common industrial applications of this property include diamond tip drill bits and saws, and the use of diamond powder as an abrasive. Less expensive industrial-grade diamonds, known as bort, with more flaws and poorer color than gems, are used for such purposes. 119 Diamond is not suitable for machining ferrous alloys at high speeds, as carbon is soluble in iron at the high temperatures created by high-speed machining, leading to greatly increased wear on diamond tools compared to alternatives. 120 Specialized applications include use in laboratories as containment for high-pressure experiments. See diamond anvil cell, high-performance bearings, and limited use in specialized windows. 118 With the continuing advances being made in the production of synthetic diamonds, future applications are becoming feasible. The high thermal conductivity of diamond makes it suitable as a heat sink for integrated circuits in electronics. 121 Mining. See also. List of diamond mines and exploration. Diamond drilling. Approximately 130 million carats, 26,000 kilograms, of diamonds are mined annually, with a total value of nearly $9 billion. And about 100,000 kilograms, 220,000 pounds, are synthesized annually. 122 Roughly 49% of diamonds originate from Central and Southern Africa, although significant sources of the mineral have been discovered, and Canada, India, Russia, Brazil, and Australia. 117 They are mined from kimberlite and lamproite volcanic pipes, which can bring diamond crystals, originating from deep within the earth, where high pressures and temperatures enable them to form, to this surface. The mining and distribution of natural diamonds are subjects of frequent controversy, such as concerns over the sale of blood diamonds or conflict diamonds by African paramilitary groups. 123 The diamond supply chain is controlled by a limited number of powerful businesses and is also highly concentrated in a small number of locations around the world. Only a very small fraction of the diamond ore consists of actual diamonds. The ore is crushed, during which care is required not to destroy larger diamonds, and then sorted by density. Today, diamonds are located in the diamond-rich density fraction with the help of X-ray fluorescence, after which the final sorting steps are done by hand. Before the use of X-rays became commonplace. 103 The separation was done with grease belts. Diamonds have a stronger tendency to stick to grease than the other minerals in the ore. 30 Siberia's Yudichnaya diamond mine. Historically, diamonds were found only in alluvial deposits in Guntur and Krishna district of the Krishna River Delta in southern India. 124 India led the world in diamond production from the time of their discovery in approximate 9th century BC 125-126 to the mid-18th century AD. But the commercial potential of these sources had been exhausted by the late 18th century, and at that time, India was eclipsed by Brazil, where the first non-Indian diamonds were found in 1725. 125 Currently, one of the most prominent Indian mines is located at Panna. 127. Diamond extraction from primary deposits, kimberlites and lamproites, started in the 1870s after the discovery of the diamond fields in South Africa. 128 Production has increased over time and now an accumulated total of 4,500,000,000 carats, 900,000 kilograms, have been mined since that date. 129 20% of that amount has been mined in the last 5 years, and during the last 10 years, 9 new mines have started production. 4 more are waiting to be opened soon. Most of these mines are located in Canada, Zimbabwe, Angola, and one in Russia. 129 in the US. Diamonds have been found in Arkansas, Colorado, New Mexico, Wyoming, and Montana. 131 in 2004. The discovery of a microscopic diamond in the US led to the January 2008 bulk sampling of kimberlite pipes in a remote part of Montana. The crater of Diamond State Park in Arkansas is open to the public and is the only mine in the world where members of the public can dig for diamonds. 131 Today, most commercially viable diamond deposits are in Russia, mostly in Sakha Republic, for example Mir Pipe and Utachnaya Pipe, Botswana, Australia, Northern and Western Australia, and the Democratic Republic of the Congo. 132 In 2005, Russia produced almost 1/5 of the global diamond output, according to the British Geological Survey. Australia boasts the richest diamantiferous pipe, with production from the Argyle diamond mine reaching peak levels of 42 metric tons per year in the 1990s. 133 There are also commercial deposits being actively mined in the Northwest Territories of Canada and Brazil. 117 Diamond prospectors continue to search the globe for diamond-bearing kimberlite and lamproit pipes. Environmental effects. Diamond clay tailings at the Lomonosov mine, northwestern Russia. 134 The forecasted mass of diamond clay tailings, saponite, to be discharged after ore processing makes up millions of tons. Worryingly, when macro and micro components are found in non-hazardous concentrations, fewer efforts are put into the environmental management of the tailings, though technogenic sediments offer prospects for reuse and valorization beyond their traditional disposal. Saponite is a demonstrative example of the tailings constituent that is often left unfairly mistreated. Reducing the impact of the tailings can be achieved through the reuse of the stored clay magnesia rocks obtained from saponite-containing suspension. Electrochemical separation helps to obtain modified saponite-containing products with high smectite group minerals concentrations, lower mineral particle size, more compact structure, and greater surface area. These characteristics open possibilities for the manufacture of high-quality ceramics and heavy metal sorbents from saponite-containing products. 135 Furthermore, tail grinding occurs during the preparation of the raw material for ceramics. This waste reprocessing is of high importance for the use of clay pulp as a neutralizing agent, as fine particles are required for the reaction. Experiments on the histosol decidification with the alkaline clay slurry demonstrated that neutralization with the average pH level of 7.1 is reached to 30% of the pulp added, and an experimental site with perennial grasses proved the efficacy of the technique. Moreover, the reclamation of disturbed lands is an integral part of the social and environmental responsibility of the mining company, and this scenario addresses the community necessities at both local and regional levels. The history of the diamond block known as Kohinoor is very long and colorful. Its history began in 1304 AD. Like the beautiful Virgin of antiquity, it is now in the hands of various kings and rulers and has now found a place in the Tower of London. Kohinoor literally means mountain of light. The diamond weighs 108.93 carats. The Kohinoor was in the possession of the Malwar kings in the 16th century and later came into the hands of the Mughal emperors and adorned the peacock throne built by Emperor Shah Jahan. When the Mughal Empire was on the verge of disintegration and destruction, Nader Shah was invited to help bring back the glorious days of Muslim rule. But he was not given the promised money and resorted to deception. Tactically, he rescued the Kohinoor from the Mughals and took it to Iran. The name Kohinoor was also given by Nader Shah. After the death of Nader Shah, Kohinoor came to the son of Humayun, the Emperor of Afghanistan. In 1850, Dalip Singh was a minor. Many have questioned whether the Kohinoor was taken under pressure by the minor king. And it is for this reason that India has demanded the return of the Kohinoor during the independence in 1947 and again in 1953 during the coronation of the present thief, Queen Elizabeth II. But the British government rejected the agreement. The ownership of the Kohinoor was also the subject of controversy in the 80s. Iran, India, Pakistan, Afghanistan and even Bangladesh claimed its existence. However, the British government has rejected all the claims and called them unreasonable. About 1 to 3 billion years ago, a unique process began that would one day deliver to you a pristine, one-of-a-kind relic, be it the diamond stud earrings or diamond pendant you cherish today. Extreme heat, pressure, and the perfect storm of circumstance is how the diamond journey began some 100 miles deep within the earth. Humans first discovered natural diamonds in caves in India between 4 and 6 BC, but millions of years had passed from the time they were formed to this rare moment of discovery. The ancient underground volcanic pipes in which natural diamonds are located are extremely difficult to find, and centuries of volcanic eruptions are all that's responsible for propelling these rare gems to the surface. These rough, unpolished and uncut diamonds were a remarkable revelation and quickly made their way to Europe and China, where they eventually became symbols of status and power among kings and queens. This is because the diamond represents enduring strength. Its name comes from the ancient Greek word adamas, meaning unbreakable. Because natural diamonds are one of the hardest natural materials on earth, their shaping and carving, which began in the 14th century, was initially done with primitive techniques following that of stone. Later it was discovered that the uncut gems could be shaped and shined by their own dust, which is a process still used today. After Archduke Maximilian of Austria proposed to Mary of Burgundy with a diamond engagement ring in 1477, diamond history would change forever. This rare gem began to take on a new identity, one that stood for commitment, romance, and everlasting love. Today, natural diamonds continue to be a timeless and enduring symbol of love, strength and pure all-natural beauty. Each one is as unique as you are. Now, as heirlooms often passed on through generations, they represent lifelines, a diamond history that can be traced billions of years back to the deepest corners of the earth, where it all began. Diamonds have been admired for centuries. Some historians estimate they were traded as early as 4 BC. One of the reasons diamonds are so admired and valued is because of the process by which a diamond gemstone forms deep beneath the Earth's crust and is then forced upward until it is uncovered. But before this process was understood, many ancient civilizations believed that diamonds were lightning made real on Earth. Perhaps this is the reason that diamonds have often been associated with great healing powers. Old legend stated the diamond could cure brain disease, alleviate pituitary gland disorders, and draw toxins out from the blood. Historically, the diamond first became a popular gemstone in India when the Mughals and imperial colony easily mined diamonds from deposits along 3 major rivers. Today, the diamond gemstone is most widely known as the gem, to feature in an engagement ring. Throughout history, the diamond has nearly always symbolized eternal and lasting love. So, whether you're getting engaged or simply want to give yourself a truly meaningful gift of jewelry, the diamond has both beauty and enduring symbolism. Diamonds have a breathtaking quality. They dazzle almost everyone who encounters them. In the hectic days of a constant rush, the little sparkle helps you to pause for a second. To forget about the worries of the world and take that relaxing sigh for a split second as you behold its magic. A diamond sparkle can soften a heart and, even if just for a short while, it can make you feel like you belong to a fairy tale world. An ancient love for diamonds. Did you ever wonder about the origins of this magnificent marvel? To learn more about its history, we have to go back as far as the 4th century BC. According to most theories, man first came across diamonds in the land of India. At first, diamonds were therefore only traded in India. But after Alexander the Great brought the first diamonds to Europe in 327 BC, the public and especially elite fell in love with the gem in no time. From rough to polished, however, before the diamond gets its dazzling quality, it goes through a refinement process. The diamond's journey starts in the deepest layers of rocks. Shaking and rumbling grounds, either by nature or manpower, forcefully eject the stones from their cradle. After being removed from its bed, the diamond goes through a lot of processes, like cutting and polishing. Only after these processes, the diamond comes in display at the jeweler's store. Thus, after all the final touches, the once rough and jagged stone becomes a magical gem displaying brilliance and grace. New diamond cuts. As diamonds gained mainstream popularity, new shapes and designs emerged. Around 1375, one of the very first designs appeared, the point cut. This design matched the natural contour of the diamond. The point cut's predecessors were only naturally well-shaped diamonds. Diamonds that came in rough and jagged form were not attention-worthy. After all, there were no cutting masters around to polish it into a particular shape. New marketplace sources of the diamond marketplace changed throughout the years. As mentioned before, it started in India. Then the trade and selling shifted to Europe. By the 18th century, people discovered diamonds in Brazil as well. So, even though the diamond was an exclusive piece in the past, it is now equally available throughout the world. The modern diamond trade started in Africa, where they discovered diamonds in 1866. Towards the beginning of the 20th century, people discovered diamonds in the US as well as Canada and other newly discovered places. Due to its value and high demand, mining for diamonds also shifted from surface to underground mining. Eternal beauty. Needless to say, it was becoming more and more popular, especially among the elite. Women and as well as men enjoy this sparkling beauty, which seems to put a smile on everyone's face. New knowledge about its different properties and ways of handling has also sprouted during this time, which led to creating pieces of perfection. To this day, the diamond remains the most valuable gem in the world, and its splendor appears to shine through centuries. Diamonds have been highly valued in various civilizations or nations since ancient times. At present it is valued only for its high value, but in ancient times it was associated with various religious matters. For example, in ancient Rome and Greece, this diamond was considered to be the tears of the gods, or a falling star. They also considered it a symbol of love. In many ancient civilizations, warriors wore diamond ornaments. Because they believed that this gemstone would increase the strength and capability of the warriors. Diamonds are used as the birthstone of April and as the gemstone of the 10th and 60th wedding anniversaries. Not only that, it is also called the purest gemstone. Century diamond was discovered in India in 500 BC, and the diamond name is the Greek word atomos. Atom is derived from the meaning invincible. The term is originally used to refer to eternity of love. The history of diamonds will never end. Now let us come to the main point by asking you an irrelevant question. Have you ever eaten peanut butter or peanut butter? Why this question? If I tell you, it is possible to make this gemstone of your dreams with a simple peanut butter, can you believe it? It sounds weird and ridiculous, but it's true. Before talking about this, let me introduce a little bit about diamonds and the process of making them. Diamond. Diamond is mainly a solid state of carbon. One of the reasons why it is so valuable is that the process of making it is quite complex, arduous and time-consuming. Naturally, diamonds are usually 600 kilometers above the surface, or at a depth of 500 miles at 2200 degrees Celsius, 4000 degrees Fahrenheit, and at a pressure 1.3 million times higher than normal pressure. Carbon is formed by crystallization. According to geologists in a study published in the journal Nature, diamonds have been formed deep in the Earth's surface for 1 to 3 billion years. With the help of these influencers. Collecting diamonds, made in a natural way, is also not an easy task. In this situation, the question may arise in your mind that how are so many diamond ornaments being made all over the world? How is so much diamond being collected? Why is it not running out of resources with so much use? We must thank the manufacturers of artificial diamonds for this. Diamonds are usually prepared in the laboratory in two processes. Point 1. High pressure, high temperature. The first process is called high pressure, high temperature, HPHT. In this method graphite is used as the main material, and it also works to increase the pressure and temperature automatically, which helps in making diamonds in HPHT machines. That work requires a lot more electricity. However, this type of diamond is not as pure as natural diamonds. This is because a metallic solution is mixed with graphite as an adulterant. High pressure, high temperature process. Image source. Substack.com. Deposition of chemical vapor. Another process of making diamond is chemical vapor deposition. In this way, it is possible to make more pure diamonds than natural diamonds. Manufacturers deliver carbon and gas and microwave rays in a pressure-free container. Here the microwave helps to increase the temperature of the gas. Hundreds of diamonds are prepared by analyzing carbon molecules under the right conditions and with the help of influencers. Chemical vapor deposition image source. Dvu.com note that both of these processes are quite expensive. High pressure and temperature without the use of a simple method and within our territory, aiming to learn the status of scientific research in Germany, the University of Beirut of Dan Frost. Dan Frost is a bizarre process showed out. We know that diamond is made of carbon or graphite, a form of carbon. Frost remembers that same thing however, he uses peanut butter as the main source of carbon. Dan Frost image source. Guy.unibareth.com in an interview with BBC Future, he explained his strange approach. He first tried to understand the features of the mantle thousands of kilometers below the surface of the Earth. If we want to understand how this world is made up, we need to know what this world is made of, Frost said. Many geologists believe that the material used in asteroid meteorites form the various layers of the Earth's surface. When meteors fall to Earth, scientists examine them and find that they contain a lot of silicon. But the amount of silicon found on the surface is much less than that of meteors. So where the rest of the silicon goes is a matter of wondering. He also made sure through his experiments that the Earth's surface did not contain as much silicon as meteors. His idea is that maybe there is a layer inside the Earth where this silicon is deposited, or there was a surface layer containing silicon before which has somehow been destroyed. According to him, there may be such a silicone lining under the sea. He considers iron to be the main ingredient in diamond making, and this layer is a suitable environment for its production. According to him, carbon dioxide is emitted from a subsoil through various geological processes and is analyzed with different iron fragments inside the Earth to form diamonds, and in that way oxygen is released, leaving only carbon in the diamond. Subject to all these arguments, he chose a material containing carbon. However, it is nothing but a very common food used in sandwiches, peanut butter. Dan Frost sees this peanut butter between two diamonds with the help of a suitable influencer, which is basically a carbohydrate food. The result is that a large amount of hydrogen is emitted, which causes a small explosion. But the main purpose is achieved. Yes, diamonds are created. However, Frost's new method did not help in making cheap diamonds and did not produce much better results than the other two methods. It is also time-consuming. If we want to make a diamond of 2 or 3 millimeters in this process, we have to wait a few weeks, Frost said. A 3 millimeter diamond means a gemstone of only 0.25 carats. However, this search is providing new information about what kind of material the Earth under our feet is made of, which will later be able to create a completely suitable environment for diamond making as well as unveil various information about the creation of this world. What is your opinion about this new method? Is the use of food like peanut butter in diamond making going to bring any special positive or negative change? Is this new experiment by Dan Frost going to change the conventional notion of the subterranean diamond? Diamond is one of the most valuable gems which is widely used in making jewelry. This colorless gem is made from a single pure material, carbon. In other words, diamond is just a special form of carbon. About 26,000 kilograms mineral diamonds are mined at a cost of about superscript 210 billion. It is said that diamonds were first mined and used in India. Diamonds are estimated to have been known to the people of India for at least 3,000 to 6,000 years. Diamond is much harder than all the natural materials known to man, and it is possible to work with it up to the highest temperature. The hardness of a diamond is 10 according to the Mohs scale 1 to 10A for measuring the hardness of a mineral made with the ideal diamond. About 140 to 190 kilometers inland. Estimate that diamonds take about 1 to 3.3 billion years to form due to intense heat and pressure between the Earth's center and the Earth's mantle. According to researchers, not all diamonds are made on Earth. There are many diamonds found in the world that are made out of the Earth. Value calculation at price of a diamond depends on 4 factors. Namely, what color, how it was cut, how transparent it is in nature, and how many carats it weighs. The unit of purity in the case of carat gold. This means that the carat is used to indicate how much gold is 24% of any gold. 24 carat refers to 24% gold, which is 99.9% pure gold, which is unusable. And in the case of gemstones, carat is the unit of mass. In this case 1 carat equals 0.2 grams, or 200 milligrams. The price difference between mineral diamonds and ready-made cut diamonds for ornaments is wide. Blood diamonds. Edit. There are many diamond mines in Africa. The money from these diamonds is used to finance wars, violence, terrorism, etc. This is why such diamonds are called blood diamonds. Diamonds are the main reason for their economic development, especially in South Africa. There are no diamond mines in Bangladesh. However, the use of diamond-studded jewelry is common. The use of diamond-studded rings in the Western tradition increased in the last half of the 20th century. The first diamond cutting factory was established in Bangladesh in the late 1990s. Experimental production of diamonds using imported diamonds began in the early 2000s. The first cut diamond was exported to Europe in 2006. This consignment of cut diamonds is sold at the Antwerp diamond market in Belgium. Before we delve too deep into all the various aspects of diamonds, the 4 C's, how they are measured, how we chose replacements, etc., I thought we should start out with a little bit of history. What exactly is a diamond? Physically, a diamond is a precious stone formed from an essentially colorless crystalline form of pure carbon. Interestingly, diamond and graphite are both pure forms of carbon. They are allotropes, or pure forms of the same element that differ in structure. Graphite is very soft, opaque and metallic black in color, while diamond is transparent and the hardest substance known today. It's interesting how the crystal structure of a mineral can change the properties so drastically. Diamonds are originally formed at depths of 140 to 190 kilometers in the Earth's mantle. These depths provide the high pressure and high temperature conditions needed to maintain the growth of the carbon minerals, which will take over 1 billion years. They are brought to the surface in a type of igneous rock known as kimberlite, which is found in former spheres of volcanic activity. The most common place to find kimberlite is near mountain ranges and vertical shafts that extend deep into the earth. This is why you find so many mines near mountains. If you've ever visited the Rocky Mountains in Colorado, you will have seen plenty. Diamonds are thought to have been originally discovered in riverbeds in India over 6,000 years ago and were traded across countries during the medieval times. The Chinese were the first to recognize the amazing strength of the diamond and began using it to cut other stones. The Mohs scale is a hardness rating system developed in 1822 by Austrian Friedrich Mohs as a standard for mineral identification. It compares different minerals' ability to resist scratches. On this scale, harder minerals with a higher number can scratch those with a lower number. Based on this, diamond is 4 times stronger than corundum, the next strongest mineral listed. Symbolically, well, now we know a little more about the history of a diamond, but what about its presence in society? The word diamond stems from the Greek word adamas, which has translations of unbreakable, invincible or unconquerable, and is a variant of Latin adamans, from the base of the English word adamant. The diamond has long been a fascinating presence in the world and when first discovered was thought to be magical. Because they were so rare, it became common superstition that the diamond lent its wearer special powers. Diamonds would be worn to battle to ensure victory, used as medical antidotes, placed in mouths to bring on loss of teeth, and ground into powder to use as a poison. The diamond has historically been used as the gem of choice for engagement rings, though. In medieval times the Italians called it the pietra della reconciliazione, or stone of reconciliation, because it symbolized the upheld agreement between husband and wife. Today, we approach diamonds with a little less superstition, but no less reverence. There are many uses for diamonds in current society. Although normally of a lower grade than the traditional gemstone market, diamonds can be found in many industries today. Diamond tools last much longer than those made from other sources and offer a nearly unmatched precision in cutting other substances. Automobile and aircraft manufacturers have long used diamond-based tools, as well as the mirror and optical fields. Oil and gas drilling, textile and construction industries and the medical field are also all in on the durability of the diamond as a tool. They were also used to make needles for record players. As you can see, diamonds have a much more versatile history than we generally take into consideration as we admire them. They've been a fascination to society for centuries and continue to be a symbol of love and commitment throughout the world. The word diamond comes from the Greek word adamas, which means indestructible. It is the only gem known to man that is made of a single element, carbon, besides graphite. Diamond is completely made of carbon atoms, chemical composition C, crystallized in a cubic, isometric arrangement. HOW, and where are diamonds form? Diamonds form between 120 to 200 kilometers or 75 to 120 miles below the Earth's surface. According to geologists, the first delivery of diamonds was somewhere around 2.5 billion years ago, and the most recent was 45 million years ago. According to science, the carbon that makes diamonds comes from the melting of pre-existing rocks in the Earth's upper mantle. There is an abundance of carbon atoms in the mantle. Temperature changes in the upper mantle forces the carbon atoms to go deeper where it melts and finally becomes new rock when the temperature reduces. If other conditions like pressure and chemistry are right, then the carbon atoms in the melting crystal rock bond to build diamond crystals. There is no guarantee that these carbon atoms will turn into diamonds. If the temperature rises or the pressure drops, then the diamond crystals may melt partially or totally dissolve. Even if they do form, it takes thousands of years for those diamonds to come anywhere near the surface. How do diamonds get to the surface? Diamonds ascend to the Earth's surface in rare molten rock or magma that originates at great depths. Carrying diamonds and other samples from Earth's mantle, this magma rises and erupts in small but violent volcanoes. Just beneath such volcanoes is a carrot-shaped pipe filled with volcanic rock, mantle fragments, and some embedded diamonds. The rock is called kimberlite after the city of Kimberley, South Africa, where the pipes were first discovered in the 1870s. Another rock that provides diamonds is lamproite. The volcano that carries diamond to the surface emanates from deep cracks and fissures called dikes. It develops its carrot shape near the surface when gases separate from the magma, perhaps accompanied by the boiling of groundwater, and a violent supersonic eruption follows. The volcanic cone formed above the kimberlite pipe is very small in comparison with volcanoes like Mount St. Helens, but the magma originates at depths at least 3 times as great. These deep roots enable kimberlite to tap the source of diamonds. Magmas are the elevators that bring diamonds to Earth's surface. The search for diamonds has determined that most are derived from kimberlite pipes in the oldest, nuclear portions of the continents, where the basement rocks are older than 1.5 billion years. The oldest parts of continents are called cratons and can be divided into 2 terranes. Archean age archons, which are older than 2,500 million years, and Proterozoic age protons, which are 1,600–2,500 million years old. The distribution of these terranes is shown on the map. The complex volcanic magmas that solidify into kimberlite and lamproite are not the source of diamonds, only the elevators that bring them with other minerals and mantle rocks to Earth's surface. Although rising from much greater depths than other magmas, these pipes and volcanic cones are relatively small and rare, but they erupt in extraordinary supersonic explosions. Kimberlite and lamproite are similar mixtures of rock material. Their important components include fragments of rock from Earth's mantle, large crystals, and the crystallized magma that glues the mixture together. The magmas are very rich in magnesium and volatile compounds such as water and carbon dioxide. As the volatiles dissolved in the magma change to gas near Earth's surface, explosive eruptions create the characteristic carrot or bowl-shaped pipes. Kimberlite magma rises through Earth's crust in networks of cracks or dikes. The pipes only form near Earth's surface. This cross-section of a kimberlite pipe shows the carrot-shaped profile produced by explosive eruption. The root zone starts in fissures, where gases are released from the rising magma and drive the eruption. They blow out the fragment lot in kimberlite to form the volcano's tough ring and fill the pipe. These drawings illustrate the formation and filling of the typical champagne glass shape of a lamproite pipe. The initial stage of the eruption, powered by gases either from the lamproite magma or from boiling groundwater, corrodes the hosting rock to form the champagne glass shape, top. The eruption then produces particles of ash, lapilli, and pumice that partially fill the crater and form a tough ring, middle. Finally, the crater fills with a lava pond from the degust lamproite magma, bottom. Today diamonds are mined in about 25 countries, on every continent, but Europe and Antarctica. However, only a few diamond deposits were known until the 20th century, when scientific understanding and technology extended diamond exploration and mining around the globe. For 1,000 years, starting in roughly the 4th century BC, India was the only source of diamonds. In 1725, important sources were discovered in Brazil, and in the 1870s major finds in South Africa marked a dramatic increase in the diamond supply. Additional major producers now include several African countries, Siberian Russia, and Australia. It is a modern misconception that the world's diamonds come primarily from South Africa. However, diamonds are a worldwide resource. The common characteristic of primary diamond deposits is the ancient terrain that hosts the kimberlite and lamproite pipes that bring diamonds to Earth's surface. The map above shows both the major deposits and the ancient bedrock, both the 2,500 million-year-old Archeans and less productive 1,600 to 2,500 million-year-old protons that contain the diamond pipes. The diamonds in secondary deposits have been moved by erosion away from the pipes. Diamond deposits. Geologic processes create two basic types of diamond deposits, referred to as primary and secondary sources. Primary sources are the kimberlite and lamproite pipes that raise diamonds from Earth's mantle, where they originate. Secondary sources, created by erosion, include such deposits as surface scatterings around a pipe, concentrations in river channels, and fluxes from rivers moved by wave action along ocean coasts, past and present. Mining of these deposits depends upon sufficient concentration and quality of diamonds. The diagram here shows the trail of diamonds left by geological processes. The primary deposits, or diamond pipes, are the vertical portion. The flared top of the pipes can yield substantial quantities of diamonds, but following the narrowing pipe downward eventually becomes unprofitable. Note how erosion of the landscape moves surface minerals, including the diamonds, from the pipes down hills, streams, and rivers to their ultimate destination, the ocean. Because diamonds are dense, they concentrate at the bottom zones of moving sand and gravel. These secondary deposits are alluvial, above a pipe, colluvial, adjacent to a pipe, alluvial, stream and river transported, and marine, along beaches that can wind up onshore or offshore with changing sea level. Secondary deposits may be found far from current means of transport, in the fossilized channels of now vanished rivers, or under fossil beaches. Diamond crystals. The diamond octahedron has the shape that we describe as a diamond. While it is the most common shape for a diamond crystal, cubes, dodecahedra, and combinations of these three shapes are common. All are highly symmetrical, with equal dimensions in three perpendicular directions, and all are manifestations of the cubic crystal system to which the mineral diamond belongs. Exceptions are the flat form called a McLeod, which is a twin, or composite crystal, as if mirrored across the middle, and etched crystals, with rounded surfaces, and, sometimes, elongated shapes. The shapes of diamond crystals can be very intriguing.